Okay, great. So last time we did shortest path, so we're going to kind of keep building on that. This is a lecture I've been waiting 6 months to give for reasons I'll explain. Okay, so is this true a week ago? I think this is true a week ago. So a week ago we started doing graph stuff, right? We did DFS and connected components and then all this topological sorting stuff. And then last time we started doing shortest path, but we focused strictly on like positive weights, non-negative weights, the unweighted case. Okay, we did breadth first search, Dijkstra's algorithm, this kind of thing. And so today we're going to incorporate some negative edges. So here's another graph. It's probably the same graph as before, and I changed the numbers. So what is the minimum distance? What is the distance from S to T? So that is the infimum over all lengths of all walks from S to T in this particular graph. Zero, negative infinity. Okay, who got negative infinity? Okay, okay. Nobody thinks negative infinity at the moment. There is a minus 10 in there, yeah. In fact, there's two of them. One of them's kind of useless. Oh, yeah. Is there an ambiguous one? Okay, if there's no number, then we'll just call it one, and then the negative three will be for the lower one. If I forgot to put a number, then it just has weight one. Right? You say right like I'm not going to affirm or in fact, I hardly ever know the answer to these questions. I just make the graph. I don't. I kind of trust you guys. There's a cycle on the bottom left. Yeah. And one also important thing is whether a negative cycle is also on the way to S to T. So even if there's a negative cycle, you want to check if it's useful for this question. You got zero? All right. Anyone else get zero? Anyone beat zero? Minus 10? Okay. Are you just like saying that? Okay. All right. Then I'll just circle vertices and you tell me which direction to go. Presumably you've had enough fun with this. Okay. All right. I'm at, oh, that was a big, I got excited there. Okay. That's too thin. All right. Goldilocks. This is just right. All right. Which way should I go? The left, the middle, right, left. That's one. Should I go down to the left or down? Down. Should I go like down right or upright? Upright. And I guess here we only have one choice. Okay, and then from here, doesn't seem like we have many choices actually. And then down. All right, so what does this add up to? 9. This is minus 10? I feel like I heard a bunch of different things. Minus 10? Oh, so it was minus 10. Okay. All right, so we beat zero, whoever said zero. Okay, but you get the idea. It's a little trickier with negative edges, maybe, I don't know. That was very convincing. Um, but let's maybe you've seen this before. But we did some algorithm last time, right? We did Dijkstra's algorithm. Uh, but it's not going to work. So Dijkstra's algorithm was sort of doing this greedy, like let's label the next thing, let's label the next thing, right? The pseudocodes in the bottom right. And so what would Dijkstra's algorithm do here, right? It'd first say, okay, this is distance 0. Then it would say B is distance 1, right? Then it would say D is distance 2. Then it would say C is distance 3, and it would happily terminate, right? But obviously going 3 to negative 2 will get you distance 1, right? So this greedy thing, this sort of next best thing, won't work. Okay? So that's one catch. The other catch uh, was negative edges, is you can have negative cycles, right? So here from S to T, it's negative infinity, because if I went around the circle once, I get distance 1. Went around the circle twice, I get distance -1. I went around the circle 3 times, I get -2. I can make it arbitrarily negative. So when there's no lower bound, we call that negative infinity. That's all negative infinity means. There's no lower bound. Okay, so those are two things we want to take care of. So in other words, this question will present a couple of funny questions that we're going to need to address. How do we deal with negative cycles? Okay. There's going to be some question about like shortest walks versus passes, which is going to come up. So before it was positive or non-negative edge lengths, there was no point in ever not taking a path, right? If you're doing some redundancy, that redundant part is going to be non-negative length. You could just remove that cycle. But here maybe, so we'll have to be a little bit more careful and distinguish between paths and walks here. Just to remind us, path means all the vertices will be distinct. And we'll be specific about that in this class, although sometimes out there in the world it's not used so specifically. And walk will be any way to get from S to T, including things that repeat and stuff like this. Okay. And at some level, we're going to have to figure out this question of what's the right induction hypothesis to make a good algorithm, because we had some kind of induction hypothesis for Dijkstra. Once I get the 5 closest, then I can get the 6 or something, right? And that doesn't seem to quite work here. So that's sort of at the heart of the discussion. So, okay, good. All right, so first we're going to, I should have erased this was okay. First, we're just going to spend a little time studying kind of distances with negative edges and just build out some simple lemmas so we can reason more clearly. Okay, so let me read this out loud. And I should have erased the proof part, but that's okay. So, let's suppose we have two vertices S and T, and suppose that S can reach T. Okay, but this is with negative edge lengths. The claim is that the distance from S to T is finite, so it's in particular not negative infinity or positive infinity, if and only if the shortest ST walk is attained by a path. Okay, so this is getting at like two of the weird things going on with this problem. What's going on with negative infinity versus not negative infinity and stuff like that. And when do you need to worry about shortest paths and shortest walks? But this lemma is saying that the shortest path will give you the shortest walk, if and only if the distance is finite. Okay, so the only time you don't worry about paths is when things become negative infinity. And so it's going to help us sort of separate these two and make it easier to reason henceforth. Okay, so it's an if and only if, so we're going to do both directions of the proof. I've already set us up on the if. So suppose there's a path from S to T that attains that shortest path distance. So there's some finite shortest path distance and it's attained, or no. There's some shortest path distance and it's attained by the walk. The claim is that the distance will have to be finite. This is not actually a hard question, so why? It's even simpler. Yeah. Yeah, I mean, okay, you have some finite path and it's giving you some walk, and that length of the distance, that has to be a finite number. Okay, so this direction is maybe so uh, immediate, and it's maybe just confusing you that I claim that we need to show it. Yeah, okay, so this part's not so tricky. Okay. All right, let's now go in the opposite direction. Suppose that the distance, the infimum over all walks is the proper definition, uh, is finite. It's some value L. Okay. Now I want to show that we can find a path from S to T with length L. Yeah. Yeah, so I think that's exactly the idea we have in mind. Let me try to frame it though, because just to get it down on paper uh, in an easy verify way. So okay, so you're kind of thinking like, oh, it's not, we should be able to get rid of the redundancy or something, right? So okay, let's let W be some ST walk with length L, and among all of those, choose the one with the minimum number of edges. There may be lots of walks, ways to get from S to T with total length L, but let's choose the one with the minimum number of edges. Okay, there's always at least one edge, so it's bounded below. So this, you always be able to get this. Okay, and we want to claim that, suppose basically by contradiction that the walk contains a cycle. It's not a path. Really, suppose by contradiction it's not a path. That means it contains a cycle. Okay. And now I want to break things down into two cases. We're going to show, oh, there must be something wrong. This can't happen. Yeah, okay. So I have one case where the cycle is positive or non-negative, and the other case where the cycle is negative. Okay. Suppose the length of the cycle is non-negative. Right. Or if it's greater than or equal to zero, then we should be able to just remove the cycle, and that's some non-negative length. It's not going to decrease anything. Right? Remove the cycle doesn't decrease the length, but it will decrease the number of edges. That actually is important to point out because that's your contradiction. W is supposed to be the minimum number of edges, but here's one with fewer edges. So that point you want to make. Okay, and then what if the length is less than zero? Yeah. No. Oh, yeah, yeah. Perfect. So just by repeating it once more will decrease the overall length, but W was already supposed to be the minimum length. There's a contradiction. Yeah. So those are, yeah. Okay, good. So, yeah, you just take it slowly and then you could tease apart some of this weirdness. Okay, so that checks off this question when we are concerned with shortest walks versus shortest path. Okay. All right, so I guess now we're at the algorithm design question. Okay, so at some level, whatever kind of implicit uh, induction hypothesis and breadth first search and Dijkstra's algorithm and stuff like that doesn't quite work, right? So we need a new algorithm idea, inductive hypothesis. They're somewhat synonymous. Not exactly, but any ideas? Yeah. Okay. Let me take it one suggestion at a time. Okay, so if I understood correctly, can I somehow update Dijkstra's algorithm? And if it updates, if it improves, just like throw it back into the pot? Uh, right. Okay, so this should. Okay, so some kind of Dijkstra's algorithm where I guess what are we doing? Yeah, so every time how do, a little awkward in terms of this version of Dijkstra's algorithm. But I guess every time you get some distance label that you update tentative distance labels, including things you've already marked. And if it improves, you kind of throw it back into the heap. And yeah, so it's just some kind of like ever improving algorithm. Okay, that shouldn't work, but why? Um, well, let's see. One issue is, I guess, what would what would that algorithm do on this? Okay, we need some kind of terminating bound. Okay. Yeah, okay, no, I don't have a great answer response. This shouldn't work, but I'm trying to think of a counterexample. Do we have the same algorithm in mind? Are we all roughly on the same page? Uh, the idea is to just kind of like adjust Dijkstra so that if some label improves, it's almost like we unmark it again. Anyone? Hmm? Well, those distance labels assigned by Dijkstra, you want to reconsider them again. So I guess maybe one problem, I mean, okay, well, at the very least, it might not be very fast. So one thing maybe I imagine is something like this. Um, okay, so I imagine first some edge going like this and then going off to some complicated graph. Okay, and then I'm going to draw a bunch of things like this. Okay, something like this. And let's say this is like length 1, and then this is like length 2, and this is like negative 1.01. Sorry, it doesn't come out very well. Um, like negative 1, just drawn it bigger. So this is like negative 1.01, so that it takes 0.99 to get there. And this would be like 2, and this would be negative 1.02 or something. Or maybe I would add some tiny epsilon or something. And then imagine all of these are really small. These are much smaller than 1. And what I imagine is I first go here, right? Dijkstra first goes here, and then explores this whole graph and gives it various labels. And then Dijkstra goes here and here, updates this guy, researches this whole graph all over again. Then, by just perturbing the edges a little bit, I go here and here, and then it goes and re-explores the whole graph and reassigns all these labels. So you're going to explore this graph again and again and again and again and again and again. And, if you want to combine that with also having some limit to check if you have a negative cycle, it might be kind of painful. And now it also feels like maybe I could start like stacking this little gadget on top of each other, if that makes sense. So in other words, this part of the graph that I just explained as some rest of the graph, it could be playing this trick over and over and over and over and over again. So like you go through and then you have to do all this crazy stuff, and then you find a small adjustment to go a little bit better, and you have to do all this crazy stuff, except all the crazy stuff is playing the same game where you first try this and you do some crazy stuff and you make a slight improvement. Yeah, so maybe you could try to start stacking this little like gadget where you find slightly better ways to get to the next point over and over and over. But if I start putting them on top of each other, the effects start multiplying. So even if there's just two, and I do it for k layers, it's going to take like 2 to the k time. Something like this. I think, does that, I mean, it's kind of vague what I described. So I guess something like this. 1, 2, negative 1.01, 1, 2, negative 1.01 kind of thing. And I chain them together, and I think it's going to explode on you. Uh, so like from here, you're going to have to do this and this. And here, you're going to have to do this and this. Here, you're going to have to do this and this, right? There's always two things you're going to have to do, and Dijkstra is always going to do the first one first. But the problem is like, so you go like this, and you explore everything, and you go like this, and you have to start over. The next time you have to go like this and like this and like this. So I think it's going to multiply with each other. It's going to be 2 times 2 times 2 times 2 times 2 times 2 times 2. Yeah. In any case, we're going to go for a much, yeah. Okay, good. I think that's a reasonable counterexample. I thought on my feet, so, good job, my instructor. Okay, I think that works though. I think that's going to give you a very hard time because I'm basically getting Dijkstra's mistakes to multiply with itself. Okay. Um, okay, good. But that was still like, I think it's worth checking why the most natural ideas wouldn't work, right? It's actually good to flesh these things out. Okay, any other ideas? Yeah. Oh, we'll get to that later. Uh, uh, we'll just get to that later, okay? So is there some way to even make all the edges positive? There actually kind of is, but that'll be at the very end, time permitting, actually. Oh, okay. Yeah, this suggestion often comes up. So in this seems to have slightly different edges from before. So let me go to the one we started with. Okay. What if I added 10 to all the edges? Wouldn't I get a positively weighted graph? And then I can run Dijkstra's algorithm, right? And I added 10 to every edge. So isn't that fair, right? Ah, okay. So a path with 5 edges goes up by 50. A path with 10 edges goes up by 100. So actually, it's going to introduce some bias. You can what? No, you can't. I mean, because Dijkstra's is just going to, it doesn't, Dijkstra's not worrying about how many edges it took to get there. Yeah. I mean, Dijkstra simply won't explore the long paths that are getting hurt more, right? Yeah. Any other ideas? Okay. So what we're going to try to do is something somewhat more conservative. So it seems a little tricky when we're trying to find the shortest path and shortest walk and trying to do something as aggressive as Dijkstra's algorithm, right? Oh, this is, I guess, what I meant to say. Okay. But anyway, I've already said it. Okay, so suppose we took a step back and we kind of solved a more general problem, which is the following. Suppose the goal is to go from S to T with at most k edges for some given parameter k with minimum total length for various values of k. Oh, can you do 1? Can you do 2? Can you do 3? Right? So, uh, and if you could do that, that seems to be on the way to getting the distances. Yeah? Okay, so suppose that was my goal, and I wanted to make a recursive algorithm. You first have to write a recursive spec. So anyone want to propose a name and some parameters? Okay, so what are the parameters? Sure, I'll just make G global. And what? And this could be this kind of thing, right? Length of shortest walk with at most k edges from S to T or something, right? Okay, I'm scribbling because I've already, okay. Here I wrote it as if we're just fixing S and we're only varying T, and that's what we'll do for this discussion, because S will always remain fixed, okay? So just for various vertices V, what's the best in 9 edges? What's the best in 10 edges to go from S to V? Okay, good. So, all right, let's implement this. We can start with base cases as usual. Okay. What should I do if f equals v? Return 0? Is that even correct? It's possible that if there's like these cycles that have, right? It's not obviously true that you always want to do that. Yeah, it could be negative. Yeah. What would be a base case? We're just trying to do some base cases, huh? Okay, what if I is 0? Oh, Ryan. What if I is 0? Okay, if S is V, return 0. What if S is not V? Yeah, we'll just write positive infinity. That's within this situation of I equals 0, right? So if you can't use any edges, you're either already there and distance is 0, or you're not there and you can't do it as positive infinity. Okay, good. So that's the base case. The general case I is bigger than 0. Should do. Yeah. Yeah, okay. So imagine you're trying to get to V, right? And you're trying to get there in like 10 edges. So you have to come from somewhere else, right? So the suggestion was, why don't we enumerate over all these edges coming in, right? And try to get there in 9 edges and take one more hop. Okay, so I guess I'll write inf so I don't have to worry about infinity stuff. But if I look at all the edges like WV, uh, well, sometimes people write something like this, saying these are the edges entering V. You could also write like WV in E, because I kind of know V is already fixed, so it's just the varying the edge parameter W. Either way, we'll probably be able to understand what you're trying to say. But as for a fixed W, what's the value you're comparing? I know you said it, but I'm asking you to say it again. I minus 1. Not quite. You're missing plus length. Okay. Are you happy with that? Okay. So if I'm trying to get there at most 10 edges, I either go from somewhere else and I use that 10th edge, or I only use 9 edges. So this needs to be wrapped in a big min. So that's one infimum. And the other option is just SWV I minus 1. That means I'm not using that ith edge. Right? So our recursive spec is saying we're allowed to use at most I edges. So we should allow the possibility of not actually using the edge. Maybe it's just hard to read my handwriting. So this is the prepared one. Okay. All right. So trying to get there in 10 edges, you either come from someone else using 9 edges and take one more, or you're already there in 9 edges. Okay. Simple enough. What's the running time? Let's say you're just trying to do K. Eventually we'll plug in for K. I use dynamic programming. If I save my answers, how long will my code take? Yeah. Sorry? Oh, but assume K is given to you. K is part of the input. So our running time will be maybe K times something. So really, I think we're mostly concerned with this inner term. What's the time for computing the shortest walk for a fixed value of I for all the vertices? Okay, m plus n y. So a particular vertex, how long does it take to solve that subproblem? Yeah, so it should be like the in degree, number of edges coming in, right? Because you're just looping over this, plus like a constant. And if I take all the vertices and I sum up their in degrees, what do I get? M, I'll just be counting all the edges. So the inner sum is M time, and then the outer sum we'll just call K. And we'll plug in for K in a moment. Okay, well maybe 1 plus degree, so Km plus N. I mean, M is usually bigger than N, but yeah. This is returning a number, the length, or the distance. There's edge lengths, which are various values. So edge length could be value 5 or pi or -3. And then there's how many edges we use. And so the I refers to how many edges we use, but trying to get the minimum sum of weights. Yeah, good question. Right? But somehow, we had all this weird stuff about like negative cycles and all these things that Dijkstra couldn't figure out. But if you take a step back and you just parameterize by a number of edges you use, you don't have to worry about this at all. Right? This is a relatively straightforward algorithm. Ah, okay, good. Good. So that's the next part. Okay. So I was probably supposed to erase this. It's okay. I'll just leave it there. Okay. So suppose there's no negative infinite distance, right? There's no cycles. Then how would you get the paths, the distances? What do you need to take k to be? Total number of edges? Which one? M? Can you do better than M? M minus 1? Can anyone do better than M minus 1? So what was that lemma we did earlier? We showed that if the distance is finite, then it's attained by a path in particular, right? How many vertices can be in a path? N vertices. So how many edges? N minus 1. Sorry, I misheard where it came from. Promosa. Okay, so actually, just running it n k equals n minus 1 should be enough if there's no negative cycles. Okay, so if you're promised there's no negative cycles, then it should take you m times n minus 1 time. By the time you've done n minus 1, you should be able to figure everything out. Okay, but of course, what if there was a negative cycle? How would you know? Okay, so at some level, like it shouldn't improve. Nothing should improve, and if something's improving, then something is fishy, right? Okay, so all we're going to do is we're going to try to tease that out and really fully explore this, right? So if there was no negative cycles, you should be done after n minus 1 rounds because you've explored all possible paths. And if you're improving after that, something must be wrong. There must be a negative cycle. But like, how long should you run it? If you went out to 2n steps, or is n enough? N should be enough. Is that obvious, or is that just like your gut feeling? Well, I don't know. You're walking around, you have to find a negative cycle, and you have to work your way through the negative cycle for something to improve or something, right? Is it obvious that like at n is enough? That would make time. I mean, if you didn't improve at n, does that mean you're done, for example? So one suggestion was you need to go out to 2n. But one could say, oh, maybe you should go out to n squared. I mean, I feel like there's many possibilities. Look, yeah. I think it has nothing to do with pigeons. Okay, let's take a vote. Okay, I'm going to give you four choices. Choice one is n is exactly enough. Okay? The next choice is some value between n and 2n is enough. And then some value, when the next choice is 2n is exactly enough. And the last choice is something bigger than that. than 2n. Okay, so n, between n and 2n, they're bigger than n. Okay, so I'll make a table. We're going to have a vote. Okay, do the four choices make sense? N. N is number of vertices. Okay, and then your last choice is you're not voting. So first of all, who's not voting? Okay. All right. Who thinks it's going to be n? Okay, this is like the only class I've ever been able to count exactly. Who thinks it'll be some value between n and 2n, like n plus 1, maybe, I don't know. Any value in between. 1, 2, 3, 4. You got to vote. Like, we don't have half votes. It's going to create a lot of problems. Okay, who thinks 2n? Okay. I didn't count. Okay, who wants between n and 2n? Okay. All right, who wants to go with 2n? Okay. And who thinks it's going to be something bigger than 2n? Okay. 10, 13, 14, 15. Did everyone vote? Oh, maybe everyone voted. Okay, I don't even get to use my favorite joke. Okay, that's fine. Um, okay, all right, good. So you've all voted. N was the most popular. Any intuition behind that? Yeah. What's true? Well, but like, suppose you ran this algorithm we just did for n iterations, and suppose nothing improves on the nth round. Then do you just conclude that you're happy? And what if some? Okay, all right. Well, let's just go through it. Okay, so well, what if it's much bigger than n? Anyway, it's always dangerous to ask why does it matter in a class. Uh, okay, uh, let's just go through this slowly. Okay, wait, it matters because it's good for your soul. Yeah, maybe. Okay, so that's the intuition behind 2n. It feels like if you have some end cycle, you have to loop all the way through a second time maybe to realize that, because if it's like positive, 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 negative, positive, 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 you need to get to that negative edge a second time in order to start realizing some things of, afoot. Yeah. Oh, okay, counter argument then. Okay. Okay, let's just do this. All right, so what I've done here is I defined AK to be the vertices whose distance improved in the kth round. Okay, so that length, SWVK, is less than SWVK minus 1. So really, that 10th edge helped for this vertex. Okay. Now, okay, so our lemma implies that any vertex that improved in the nth round must have what distance? So you run it n minus 1 rounds, you run it one more, and this vertex's distance went down, or its distance value, SWVN, is smaller than SWVN minus 1. That lemma we did at the beginning, what does it imply? It must be negative infinity. So all of those are negative infinity right off the bat, right? And uh, in fact, that doesn't just hold for the nth round. If anything improves in any round after n minus 1, it must be negative infinity, right? But there's still some question of like, how many rounds do I need to go to make sure I got everyone? I figured out everyone who's at distance negative infinity, things like this. Okay, so Right. So how do I at some level identify sort of this infinite set, everyone who improved in every round after n? That would eventually capture everyone, right? Okay. So good. All right. So let's just take it simple. The first lemma, the first claim is that everyone who improved in round 11 must be must be kind of they must have some in neighbor who improved in round 10, right? Because each round I only look at the in neighbors, right? And I kind of see their current value and then add it. And if none of those values change, I'll just come to the same conclusion as the last round. Okay? So, okay. So that's the intuition. So, so what does that mean? That means that like am plus 1 is within the out neighbors of am, right? So whatever improved in the 101st round must have an edge from somebody who improved in round 100. Okay? Same with am plus 2. Okay? Must be something that improved in 102 must have been coming from someone who improved in round 101, which must be one hop away from one improving in round 100, right? Like this and so forth. Okay? So what does that mean, right? So our goal is to figure out everyone who improves after round n minus 1, so round n and beyond. But how can I sort of find that efficiently? Suppose you had an, and I want to get everyone else. Huh? I hated chemistry, so that's not a compliment. Okay. Oh, yeah, that's true. That's true. Um, okay, well, let's put it this way. Okay. If this vertex ever improves after round n, then it must be reachable from somebody that improved in round n, right? Because of this neighborhood kind of growing process, right? Okay, so now that I know that everyone I need to find is reachable from someone who improved in round n, okay? And conversely, suppose somebody is reachable from someone in round n. So there's a vertex that improved in round n, and there's a way to get to me. What do I know about the distance to me? Huh? But what about the distance in terms of the edge lengths? What is the distance from me, from S to me, knowing that some vertex that improved in round n can reach me? Sorry? Sorry? It's going to be negative infinity, because you can get to me from someone else who has negative infinite distance. Okay, so if you can reach someone from an, then their distance must be negative infinity, because I can get to layer n, is a negative distance, and then find my way over. Okay, so we put all these things together. Uh, so you really only have to run Bellman-Ford for n rounds, and then you can just do like DFS, BFS from the guys who improved. Right, it's just one BFS or DFS. Okay, so right, so once you've run this algorithm for n rounds, then you can basically read off who has negative infinite distance. Okay, by just doing one more who can be reached. Okay. All right, good. Okay, so put that all together and you get mn running. Okay, and then you also be able to sort out not just the finite distances, but everyone who has negative infinite distance. Okay, you run it for n rounds, you do one breadth first search, depth first search. After that, figure out everyone who's negative infinity, and that's everything. Mn time. Okay, so the answer was kind of n, but you do need to do a little BFS or DFS. Okay, it's like a fixed point argument. Okay, good, good. All right, so I want to mention something. So this algorithm is called Bellman-Ford, but it's really due to four people, uh, whose names sort of escape me. Okay, but it's from the 1950s. Okay, it's like 1955, 56, um, and it was really, really old. And this is a really, really basic problem. So I think we all kind of thought this must have been the best algorithm. Okay, but only like last year, a little more than a year ago, uh, somebody showed how to get an mn to the eighth nine running time. Yeah, it's sort of a complicated algorithm. Okay, but it's not doing dynamic programming. It's doing something much more sophisticated. Uh, but I think this was really exciting because we've all stared at this and taught this year after year after year after year. Everyone's teaching this across the world, right? And we can still get improvements on this uh, basic problem. Okay, so it's relatively exciting. Uh, the reason they put a tilde on top of the O is because they don't even mention the logarithmic factors. Like they're just worried about getting a better polynomial, and they're not really worried about getting the best logarithmic factors because, high order and lower order terms. So they just hide it by putting a tilde there. The actual logs aren't that bad. It's probably like log to the fourth or something. But he wasn't trying to optimize it. He was just trying to improve the n to the 8 ninth. Yeah? And just for fun, a slight humble brag, but like just for fun, with your TA and another PhD student, we worked on trying to improve this paper, and now you can actually do mn to the 4/5. Yeah, so the actual record for this problem is currently mn to the 4/5, and it's obviously not the right answer. It's just the best answer we have right now. Yeah, but I mean, the only point I want to make is not that I worked on this, but it's just that like even these really old problems are potentially improvable. The Dijkstra's algorithm is going to be very hard to improve because it's quite fast. M plus n log n, you're not going to do better because it's already. But a problem like this, as old as it may be, there's no reason why someone in this room couldn't improve it. Yeah. Okay, cool. Okay, good. So, yeah. Yeah, so in a cycle case, I think this they were imagining something where you have a long cycle with positive edges and a very big negative edge at the end. And then you realize negative cycle. What this algorithm would do is go all the way around, and then after n iterations, it'll take that big negative edge, and it'll get one. Yeah, S will improve, right? Because you're going from S all the way around, and then to the distance to S will improve. And then from there you do reachability from S. So S will be that vertex in AN that improves, and then your reachability will find everyone else. You go to S. Yeah. I think there's no interesting lower bound. There's no reason why it couldn't be M. It just seems very tricky. I mean, like the dates, right? Like this happened in July. So like suffice to say, I've been thinking about it a lot since July. I haven't improved it. So yeah. Yes. Yes. But it can get arbitrarily small, right? So distances are just worried about like in the limit. So here we're just going to classify things as negative infinity if it's anywhere on this cycle because it can go arbitrarily small, if I understood your question correctly. So like the cycle referred to in the back, uh, why is it even a problem? Well, that's hard to interpret because we just showed it's not a problem. But like, I'm not sure if I understood the question actually. Yeah, so the algorithm isn't just saying, oh, I found a negative cycle, I'm done. It's actually identifying everyone who has distance negative infinity as well, if in case that was a point of confusion. All right, other questions about this or that? Anything's fine. Okay, good. All right, so that was negative length. Now we're going to do all pairs shortest paths. Okay, and for simplicity in discussion, I'm going to assume there's no negative cycles. I'll allow negative edges, but no negative cycles. If you want to detect a negative cycle, one thing you can always do is you can add a super source vertex S, okay, connected to everyone with length 0, and then do the algorithm we did before. Okay, so if there's any negative cycles, then there will be negative infinite distance from this super source you've added to someone. Okay, so detecting negative cycles is not that bad, and our algorithms are going to be like no faster than that pre-processing step. So we're just going to assume no negative cycles. Okay, good. So I think, okay. All right, so if we take what we did before, right? In fact, the initial suggestion for recursive spec actually had S and T in it, right? So that seems like a reasonable idea. Why don't we do that? Okay. So my recursive spec was do the source, the destination, number of edges, and say what's the length of the shortest walk from S to T was at most that many edges. Same as before, but I'm now allowing S to vary in addition to T. Okay. All right. Let's implement this. Who wants to start? In the top right, it says essentially same code, so it shouldn't be too bad. Yeah. Okay. And then what if I is bigger than 0? Yes, I think this is probably similar. So, okay, I'll just look at all the edges that are going into T. Now they're called U for some reason. And I'll say, okay, how can I go from S to U in I minus 1 steps, and then take one more edge from U to T? Okay, but this is doing it for all S's. Okay, what's the running time? If I do this for all the way up to I is equal to N, because we know N is enough. N cubed. Okay, so I think you're saying that there's N choices of S, N choices of T, N choices of I, but one of these algorithms takes how, or one of these subproblems takes how long? There's N cubed subproblems, but like how long does that loop take? N squared M, so because we're going to sum over the in degrees of T again. So for a fixed I and fixed S, I'm summing over all the in degrees of T. So I get N times N times M. Again, apologies for the most confusing notation in the world. I mean, I apologize, but I don't change it, so I think it's not a real apology. Okay, so mn squared. Okay, all right. Can we do better without changing the algorithm too much? There's a trick. Same high level approach. Can we do better? Let me give you a clue. So what we did last time was we kind of figured out the last edge to add, right? We picked some u that comes right before t. Is there a better kind of way to divide things up? Yeah. Look at the vertex. Okay. So instead of looping over these edges, I would loop over all the vertices. Oh, okay, sure. But I'll point out that then you'll have n choices for I, n choices for S, n choices for T, and for each subproblem you have a loop of size n, because you're looping over all the vertices. And that gets you to n to the fourth, which is not going to be any better than mn squared, because m is at most n squared. Okay, so let's say I want to figure out the best way to do one edge, you know how to do that. If I want to figure out the best way to do two edges, I try to figure out that vertex in the middle, right? Okay, suppose instead of three, I try to figure out the best way to get from S to T with four edges, or at most four edges. I've done one, I've done two. How do you do four? Yeah, so what would you do? Yeah, I could try to guess the middle vertex that's coming after two edges and use the things we computed for the two distance. And then once I have four, I can try to do eight. That was supposed to look like eight. Uh, and I could try to guess what's four in the middle after four steps. In four steps. Okay. So, okay, so we can do something. I'll just write it out like this. So at some level, I is sort of getting replaced by two to the I. I'm just trying to do powers of two. Okay. And it's actually very close to the suggestion of looping over the vertices. But the key point is I'm trying to loop over the middle vertex, not the preceding vertex. Okay. So if I'm trying to get from S to T in 2 to the 10 steps, I'm going to loop over all the vertices U and say, what's the best way to get from S to U? And at most 2 to the 9 steps. And then from U to V, or U to T was 2 to the 9 steps. Okay. All right. So now what does our running time become? How many of choices of S? How many choices for T? And then how many choices for I that gets plugged into 2 to the I? Log n. So I only need, or actually log m and log n come out the same basically anyway, up to a factor of 2. But I only need to go from 1 to n, so I equals log n is enough. Okay? And then for each subproblem, how long does it take? N is just looping over all the guesses of middle vertex. So I get n cubed log n. Yeah, so this is called a doubling trick. And doubling tricks are very clever and shows up in lots of situations. So always check to see if there's a doubling trick in your given problem. I think we discussed a doubling trick before when we talked about exponentiating matrices. Okay, good. Um, okay, we're going to do another algorithm. I'm not really sure if this is a very helpful slide. Uh, does anyone want to suggest any other crazy ideas for all pairs shortest paths? We're actually going to do a slightly faster algorithm by sort of a different recursive spec, but I don't know how guessable it is unless you know the answer. Yeah. Oh, can you do some kind of pre-processing and prune? Um, it seems sensible, but it's tough, because you're doing all pairs shortest paths. So an edge that's useless for one could be useless for another. It's not clear you're going to be able to get rid of many edges. Oh, just BFS from everyone. We can assume there's no sinks then, and then you're still stuck. Yeah, could be helpful, but won't help us asymptotically in the worst case. Okay, I'll just get to I don't know how this is guessable. Okay, well, here, or at least here's a hint then. Suppose I index the vertices v1 to vn, okay? And I want to come up with some kind of recursive spec. It's probably not a helpful hint, actually. Yeah. Oh, okay, well, there's the answer. Um, okay. So, oh, this should be right. So let's get the length of the shortest walk from VI through VJ, but the intermediate vertices are only from V1 to VK. So it's limiting which vertices you can use in the middle. In each iteration, you're allowed to use one more, midpoint. All right, so who wants to implement this? That's okay. So the V1 to VK is only referring to the vertices in between. It's not referring to VI or VJ. So VI, VJ could be whatever crazy big values. Let's say that like I and J are really big and K is very small. That's what you have in mind, right? So all it's saying that, you're at V100, you're trying to get to V200, and you're only allowed to use the first five vertices in between. So you're allowed to go V100, vertex 1, vertex 2, V200. That's okay. It's only limiting the vertices strictly in between. Okay. All right. Who wants to implement this? Yeah, K0 is the easiest base case. You can't use any intermediate vertices. Yeah, so if there exists an edge, then you can use it. Otherwise, positive infinity. Okay, are you guys okay with this? There's one minor exception. They're the same. Sorry, 0 if I is equal to j. Oh yeah, interesting case, k is bigger than 0. You're allowed to use some vertices. How are we going to break this down? Plus? Uh-huh. Right, okay, so the second option you just say I don't use vertex k. But the first option is saying, look, if this is vertex k, then in between, uh, in this first half, I am trying to get from VI to VK without using while only using vertices between V1 and VK minus 1. And the second half is trying to go from VK to VJ using only vertices between V1 and VK minus 1. Okay. How are you supposed to think of that? First you make a time machine. Uh, how are you supposed to think of that? I don't know. Anyone have a good answer to this? Question is, how are you supposed to think of that? I mean, I think these are very clever, good ideas. I imagine when Einstein came up with the theory of relativity, somebody out there was like, how are you supposed to think of that? Yeah, I don't know. It's a very clever algorithm, but I think, you might underestimate like what it's like to do this for a full-time job. Like, how long do you spend on a homework problem? Like an hour, 2 hours? And then you get bored, you check Google or something? Like, right? So I think you might underestimate. It takes some skill and some practice because you have to deal with being discouraged day by day, like almost every day. But I think you'd be surprised, like, what one can do if one really spends a lot of time on something, more than a relatively limited amount of time. Yeah. But I don't think this was. I think this took a while. I think the other algorithms existed for a while and was sitting for years before someone came up with this. So I don't think it's obvious. Yeah. No, that's what the second op or the first option in this version is letting you do. So ijk minus one is saying you don't have to use number k. It's letting you skip vertices. The second one you are going to k in the middle. So it's the shortest walk from I to k using the first k minus one, and then from k to j using the first k minus one. So in the second one you are visiting k. In the first one you're not. All right, what's the running time? How many subproblems? How many choices of I, j, and k? Yeah, n cubed total, n each. And how long does each subproblem take? O of one. So you get n cubed. Yeah. So these algorithms have names. I sometimes forget them, but I believe this one is called Floyd-Warshall. Yeah. Who are, smart people. They have had other successes. Was Floyd on our selection algorithm? Was there a Floyd in there? Linear time selection? Okay, whatever. Floyd's a very strong guy. Okay, we have time, kind of, not really, for one more algorithm, which actually I usually don't put in, but actually it's strongly related to some of those recent algorithms that I mentioned. So I thought I would mention it. Okay, but it's another algorithm for all pairs shortest path, and it uses a very cool trick. Okay, all right, let's say you're doing all pairs shortest path, and suppose all the edges are non-negative. You can do the n cube algorithm we did, but what else could you do? Suppose it's a sparse graph. M is much less than n squared. All the edge lengths are non-negative. You want all pairs shortest path. You could just run Dijkstra from every vertex. Every possible choice of s. I'll take it m times n plus n squared log n. If m is much smaller than n squared, that's actually better than all these clever things we've done, right? Except it only works as non-negative edges. So, okay, so that's pretty good. So the question is, can you make all the edges non-negative? Which seems a little preposterous, right? But let me show you a trick. Okay, so imagine you have some like negative edge. Okay, and imagine you start assigning some kind of like vertex potentials. Okay, they're like prices put on the vertices. And these are going to induce new edge weights, which is going to be the starting point plus the edge length minus the endpoint, which seems a little eccentric. But in this case, 13 minus 10 minus 1 will be equal to 2. Okay, yeah. So those are vertex potentials. So for every vertex, I assign some number, just a label. Sometimes they're called prices. They're not fully, huh? No, it's not really voltage. I mean, sometimes when we don't know what to call something, we call them potential. Like you have lots of potential. Okay. Yeah, I don't know. It's just some big. Okay, but we're just going to assign values. At this point, it's not motivated. I'm just doing a definition. Okay. So, okay. Now, now consider a path, right? From I guess V0 to V3. So I've annotated the edge lengths with the original edge lengths, and then above the vertices are their potentials. Okay. Now, what is like the sum distance in terms of these adjusted lengths? Yeah. Okay. So because of this plus minus action, okay, you're going to get something like this. So, okay, so I'm trying to get the length in terms of these adjusted edge lengths along the path. So I'm summing up these vertices, okay? And so here I'm breaking it down by edges, right? Phi v minus the potential of vi minus 1 plus the edge length minus the potential of vi. So potential of the ninth vertex minus the potential of the 10th vertex plus the potential of the 10th vertex minus the potential of the 11th vertex plus the potential of the 11th vertex minus, okay, so they actually cancel out, okay? So what happens is you get the original length of the path in terms of the original input edges plus the potential of the first vertex minus the potential of the last vertex. Okay. So what's cute about this idea, that means that if I reweight with potentials, I do this plus minus thing. None of the shortest paths from S to T change for fixed S and T because every path from S and T changes by the same amount. It adds the potential from S, subtracts the potential from T, and everything in the between cancels out. Okay. So I can play this game with potentials without really changing the shortest path structure. Which are the shortest paths remain the same? Okay. So the question is, and so this is a trick, from like the 70s. The question is, can we find potentials that'll make all the edges non-negative? I call that neutralizing the edges. Okay. All right. So consider this potential. Okay. This potential phi is defined for every vertex x I want to come up with a value, right? And I'm going to take the minimum over all possible starting vertices, the distance to me. Okay, we can use Bellman-Ford or something. We'll talk about how to compute in a minute. But it's what is the minimum distance to me for any starting vertex? Okay, which may not be great notation, but I'm calling D capital Vx because V could be anything in V. Okay. Okay. So look at the edge length induced by this potential, right? So I have X, I have Y in the edge length, and then the potential to X is based on some distance from some vertex to X, and the potential for Y is based on some distance from some vertex to Y. Okay. So if we plug this in, right? Okay. Now, what's nice here? So let's look at this. So the first term is the distance from some vertex to X. And then I go add the length from X to Y. Okay. Meanwhile, the subtraction term is find the minimum distance from any vertex, but from some vertex to Y. So which is bigger? The first two or the last one? First two, why? Even though the second one's bigger than the third, the first one might be negative. The first one, they could be negative numbers, right? Yeah, it is triangle. So dvx plus length of xy is a distance is a length of a walk from some vertex to y. It's just going through x. And dvy is a length of the minimum walk that ends at y. Okay, so it's a triangle inequality kind of thing. It's only awkward because the starting vertex can be anywhere. So this thing is always greater than or equal to 0. So this kind of magical potentials that'll turn all your edge lengths non-negative is actually kind of exists. All we have to do is calculate for every vertex, sort of the length of the shortest walk ending at that vertex. Yeah, but that's already quite cute, right? Okay, so next question. How do you compute these potentials efficiently? So one way is for every vertex run Bellman-Ford like we did. But that's just doing all pairs shortest path, that's not so great. So can you do something more clever? Yeah. That will work for one of the x's. Huh? Well, because you want to get the potentials for every x. That's the thing. So for every x, I want the length of the shortest walk ending at x. And this has a cute solution. It's guessable. It's not easy, but it's guessable. I want to basically do it in one Bellman-Ford. Because that would be great, right? If I get all the distances in one Bellman-Ford. So you're going to want to change the graph, not the algorithm. Yeah. Yeah, so I want to compute these potentials x. Okay? For each x, that is, what is the length of the shortest walk of any walk in the graph ending at x? Or the implement. That could be negative infinity if there's negative cycles. But for the sake of exercise, you can imagine there's no negative cycles, and I promise it'll be okay. Imagine there's no negative cycles just to make it easier to think. I want the length of the shortest walk. Yeah. Yeah, so I can add a super source, connect it to everyone, but I need an edge length. Yeah. Speak with confidence though. Zero? Okay. So I add a super vertex and I add length zero edges to every vertex. And what S star basically does is it helps us pick for every vertex X the best starting point, right? So S star will, yeah. So you're going to get these distances from S star, to each vertex, but that first edge is just going to some other edge and it's zero length, right? So you can use S star to you kind of choose that first vertex for you. That's going to be helpful for lots of tricky word problems, that trick, or similar tricks maybe on the destination side, right? And so just one Bellman-Ford will get you all these distances for you, okay? So you put that all together, you run Bellman-Ford, you get these prices, that's mn time. You apply these prices, all your edges are non-negative. Now you run Dijkstra's algorithm, mn plus n log n. That gets you all these distances, except they're slightly off by the potentials, but the potentials are easy to adjust, right? S to t, I just subtract out and add back in just the endpoints. Okay, so potentials aren't a big deal. Okay, so you put that all together, and you're going to get, mn plus n log n. Okay, so I only mentioned that some of those new algorithms trying to beat Bellman-Ford are actually trying to just compute potentials that make all the edges non-negative, even faster than Bellman-Ford. Okay, but otherwise, that's in fact what it tries to like only do square root n of the edges at the time. It only kind of makes partial iterative progress. That's what I think what Wilbert was referring some extent to at the beginning. Okay. It is. It will effective. Well, it's going to give you a similar effect, but the running time is much better because you only run with one Bellman-Ford. It's a running time issue. It's just for the sake of speeding things up. All right, I'm way over, so sorry about that. And yeah, all right, that's all. Thanks, guys.